Hello, and thank you all for joining us today. My name is Greg Johnson with Loring Consulting Engineers, and I'm a member of the Illuminating Engineering Society, as well as part of the Education Committee for the IES Raleigh section. I would like to welcome you to our presentation today on causes of excess color changes in streetlights. We have a great presentation lined up for you today, but before we get started, I'd like to cover a few housekeeping items. At the bottom of your screen, you'll see a box for Q&A. Please feel free to submit questions throughout the presentation. We'll address as many questions as time permits at the end of the presentation. Any questions that do not get answered, we'll follow up with email responses. And lastly, all of our presentations are recorded and archived on our YouTube channel, so you'll be able to view the presentations again or recommend to others. I'll place a link to the channel in the chat section as well. So today we're happy to welcome Dr. James Lynn Davis. Lynn is an independent consultant with a lengthy career in lighting and electronics technology development and has worked on new materials for advanced radio communications, tunable white lighting technologies, and the reliability of solid-state lighting devices. Lynn is a member of the IES Testing Procedures and Lighting for the Aged and Partially Sighted Committee. He is also a member of multiple committees at the Illuminating Engineers Society and a senior member of the Institute for Electrical and Electronics Engineering, or IEEE. Over the last several years, there have been numerous reports of excessive color changes in LED streetlights, resulting in a dramatic change from white to purple or blue. And I imagine most of you are here today because you've noticed these purple bluish LED lights and wonder why they appear purple. Is it an aesthetic design choice, a special consideration for local or environmental reasons, a malfunction or degradation of the LED coatings, fixture housings, lenses, etc.? I know because I've pondered this many times myself as I drive around town. In today's presentation, Lynn will provide an examination of LED light engines taken from warranty replacements of field products that exhibited visually excessive color changes. These LED light engines were characterized using a combination of visual, photometric, and thermal measurements, and the root cause of the color change was identified and will be discussed today. So without further delay, let me introduce you to Dr. James Lynn Davis.
Thank you so much, Greg. Um, I wanted to get into this topic of excess color shift in streetlights. But before we dive into that, I want to thank my collaborators, Steve Paolini from Telelumen, Morgan Pattison from Solid State Lighting Services, and Troy Trottier from Trottier Consulting. We're part of an organization called the LED Systems Reliability Consortium, or LSRC. And if you're not familiar with that, I'd like to take just a second to explain what the LSRC is. It's actually a group of industry experts, somewhere between 15 and 20 companies, and we volunteer our time, meet monthly, and work collaboratively to try and understand issues with LED lighting, including issues like luminaire lifetime and reliability, and also models for prediction of LED lighting products. If you're interested, I'll have contact information at the back of the presentation, but you can also go to this website here for more information about the LSRC. So as Greg said, this problem with the purple or blue streetlights has been around for the last couple of years, and we've noticed as you've driven around here and elsewhere, this shift from the nice white light to a pastel or a purple or even a blue light. And if you look around, you can see it in all kinds of applications. Here's a picture from a couple of years ago along the highway in Apex. This is middle one is a picture that Steve Paolini took at LAX just a couple of months ago, so the problem's still with us. And here's one I took from a residential neighborhood in Cary about a month ago. So this is a significant issue. And to give you an idea of the scope, if you just do a little Google search on the term purple streetlights and look for news stations that have run reports on this and start to map them across the country, you find that most of the country have shown this phenomenon, and even some Canadian provinces. The reason why news stations are covering this, and it was covered locally by at least two different TV stations, is because Department of Transportation's and utility companies that own these streetlights are trying to get the word out and trying to tell people about this so they can be replaced. And the reason why they want them to be replaced is there are some potential safety issues with these streetlights with excessive color shift. Primarily, you do a nice lighting design. You're expecting a certain amount of white light to illuminate the roadway, parking lot, or whatever. But if the light is turning purple, it may no longer comply with design standards like RP8. We also know that adequate color rendering is an important part of object identification. You know, whether it be another car, a pedestrian, animal, or some sort of object in the road. So being able to have good color rendering allows us to identify objects and react accordingly. And if you've driven through these areas where there's a lot of these purple streetlights, you know that it's kind of glary and uncomfortable, which could distract the driver and create some issues. And, you know, quite frankly, the automotive headlights are not really designed to compensate for this sort of imbalance in lighting. And so that might not be able to help the problem fully. So to dive into this in terms of understanding what's going on, let's start with the white LED, or a phosphor converted LED. As I'm sure you're aware, it consists of a blue LED with a layer on top of it that is made from phosphor and silicon. So it's actually a composite. And the LED manufacturer spends a lot of time and puts the right amount of phosphor particles of given size and the right amount of silicone binder in there to hold everything together and to adhere it down to this blue LED chip. And so when you turn the LED on, some of the blue light passes through voids in this silicone phosphor binder where there are no phosphor particles and will emerge as blue light. But most of it actually hits the silicon particle or hits a phosphor particle and gets converted into broad spectrum light. So you get a spectral power distribution of what we're used to seeing, where you have the big blue peak from the blue emission, and then the broad phosphor peak, which in the combination together, blue plus yellow, gives us something that approximates white light. And this is what we were expecting from our LED sources. These, of course, come packaged different ways. There's the high power LED, where there's a single pretty good size LED chip with a single phosphor silicone layer on top of it. The mid power chip, where there's a much smaller LED chip, and you might just be able to see it right here, that's sitting in a tub that's then filled with this silicone phosphor mix. So this is just like filling a bathtub. Another common package is the chip on board, which is used for high base, where you can maybe make out individual LEDs. It covers a fairly large area with a common phosphor layer over top of it. And this has the appearance of a fried egg. It's sometimes called a fried egg LED. And the fourth type that we'll spend a lot of time talking about today is the chip scale package, which is a relatively new package. In this, you take a small LED, and instead of having this big silicone phosphor mixture filled in the tub, you just put enough of the silicone phosphor to cover the top of the LED, and they're attached on the back side through flip chip, and you can get very, very high density light sources, as shown here. The high power and the mid power LEDs been around since the beginning of LED lighting. Chip on board has been around about 10 years, and chip scale packaging has really come in its own in the last 5 years or so. And between chip scale packaging and mid power packaging, that's probably the most common LED package. But we're going to concentrate on this chip scale package here today. So if we look at the silicones that are used in this, it's not just the phosphors we have to think about, it's the silicones as well. The silicones are an important part of that composite because this whole package has different materials. They expand and contract at different rates. And the silicone has to be that compliant layer that kind of holds everything together. And if it's not able to do that, if it's not able to remain plastic, you can have issues with brittleness and even a loss of adhesion. And because adhesion is such a big issue with LEDs, LED manufacturers spend a lot of time trying to make sure they get good adhesion of that silicon phosphor layer to the LED. They do a significant amount of cleaning of the surface of the LED, but they may also roughen the surface, which not only helps with light extraction, but also helps with adhering that layer to the LED dye. Now, when we think about light, we think of lumens. So lumen is actually a measure of how the cones in our eye respond to light. And so there's actually a wavelength dependence. The eye is most sensitive to light at about 550 nanometers. So if we look at the photopic sensitivity as a function of wavelength, we see the maximum is at 555 nanometers. Blue LED, the blue light from our LED, the eye has much less sensitivity, only about 5% of green at 555. The eye has pretty good sensitivity for yellow and red and orange as well. So the important takeaway from this is the LED, the blue LED, producing light that the eye really can't use. It's really the phosphor that converts that blue radiation into the broad spectral light that we need to see an object clearly. And it's also this broad spectrum that provides good color rendering. If we only had a few wavelengths, our color rendering would not be as good as if we had broad spectrum radiation. So spectrum is important for giving us lumens and color rendering. So when we measure a spectrum, we can think of it in two ways. The way that's most commonly represented is what I've shown on the left, and I showed this earlier, where you have a power distribution. So the y-axis is actually radiant flux or power in watts, and the x-axis is wavelength. And you can see here's the blue peak and the phosphor emission. But what the eye actually sees is in lumens. So I can convert from watts to lumens by using that photopic sensitivity curve and a scaling factor. And what the eye actually sees is this, a little bit of a blue peak and a lot of emission from the phosphor. So it's also important to know that if I take the integral under these two peaks, and the spectra are exactly the same, it's just one is in watts, one is in lumens. If I take the integral, in this case, my integral is going to be radiant power. So this is the total power that my device is emitting. And on the right, this integral is the total luminous flux that my device is emitting at all wavelengths. So those are important concepts to keep in mind. Also want to touch briefly on chromaticity diagrams because that'll be central to our discussion. There's two main types of chromaticity diagrams that you've probably seen. The 1931 diagram is probably the most common. In this, chromaticity is represented as an X value and a Y value. The other common chromaticity diagram is the 1976 diagram, where chromaticity is given in U prime and V prime. To convert between the two is simple math, but the reason why there are two is this initial chromaticity diagram actually distorts color perception. Distance, I could travel a long way in this direction and not be able to see much of a color change, but if I go a short way in this direction, left to right, I could see a big color change. Whereas in the 1976 diagram, distance is roughly equal to the amount of color change. And that's why people use it, because it has better perceptual uniformity. A couple of other features just to point out of this diagram is these numbers along the edge, 440, 460, so forth. Those are monochromatic radiation. So a 450 light source would be about here in the lower left-hand corner. And the other point to pay attention to is this line that goes through the middle. This has numbers beside it, 3,000, 4,000, so forth. This is the Planckian locus, sometimes called the black body locus. And white light would have chromaticity coordinates somewhere around this Planckian locus. You should be very close to it, very, very close. What you will notice is when you start mixing wavelengths, you can get a variety of different colors: blue, green, reds, even purples at certain combinations of colors, as we'll see. So specifically, if we look at a white LED or a phosphor converted LED, we have the blue LED base that is emitting at about 450 nanometers, and it has this broad spectrum emitting phosphor that has an average wavelength of somewhere around 580 nanometers. And I can actually draw a line between these 2 points on the chromaticity diagram. And by changing the amount of this blue light and yellow light that I have in my light source, I can move anywhere I want along this line. Now, LED manufacturers are very meticulous about choosing the right combination of blue emission and yellow emission to get right on this Planckian locus. And if they get too much yellow, it starts to look a little yellow. If they get too much blue, it starts to head down into purple and blue. So if you think about what is changing, what to look for to see this type of changing, you can look at the chromaticity coordinates, the U prime and the V prime coordinates of the source, and see how that changes with time. And you see in this case, the change is primarily in V prime. It's mostly changing V prime. It's going from about, say, 0.5 to 0.05. So a significant change in the V direction, but not a whole lot of change in the U prime direction. So if I wanted to track this, I could actually look at how my delta V prime is changing with time. So let's dive into these samples. I hope that's what everyone came for. So what we received were 28 LED modules that were warranty replacements that we received from North Carolina Department of Transportation. These devices, we believe, were installed somewhere in 2018. We got them in 2023, so they had been operating for 4 to 5 years. If you take these LED modules apart and look at the board codes on the LED boards, the board codes are from the middle of 2017. So we know when these were made and about when they were incorporated into fixtures. And the samples that they came from, a couple of different types of street lights, but these have also been seen in parking lot lights and other types of lights as well. They may have 2 of these LED modules in a fixture, or 4, as you can see here, and some even have more than that. So if we look at these modules, the individual modules, each module has 20 CSP LEDs. There's one underneath each lens here. They're all connected in series. And if we look up the specs for the LEDs, these particular LEDs are rated at 2,000 milliamps and operation at 125 degrees C. So the LED manufacturer is expecting these devices to be pretty robust. The fixture manufacturer is not pushing them to the limit at all. He's only designing his fixture to operate at about 700 to 1,000 milliamps. This LED module actually is very well made. It's a copper-cladded dielectric layer on a thick aluminum plate with a graphite heat spreader on the back. And I've got a picture of one right here. It's about 6 inches across and 8 inches tall, or I'm actually holding a sample. Very well made, very rugged, very solid. The lens is held in place. These lenses are held in place by this white frame with a silicone gasket behind it. And there's a lot of precautions in this design to deal with managing heat and to prevent damage from lightning. So I want to dive into the samples that we actually have, and we'll go through several of these. We won't go through all 28, but this is LED module 1, and it chose this because this was the best one that we had. If you start in the picture in the middle, you'll notice this is a pretty good white light. Everything seems to be going okay. If we look at the chromaticity coordinate of this source, it's close to the black body, as you can see right here on the left. It's very close to the black body. And in fact, if you measure the distance of this color point to the black body at 4,000 Kelvin, that's called delta U prime V prime, which is the magnitude of the color shift. It's about 0.009, or sometimes called 9 steps or 9 McAdam ellipses. And while that may seem like a small number, it's actually pretty significant. If I had a 4,000 K source that was exactly on the black body and this source and put them side by side, I could tell the difference between them. I may be able to use this light, but I could tell that there is a difference. And in fact, the general rule of thumb is that color changes become visible. I can tell a difference when this distance, delta U prime V prime from the black body, is greater than 0.007. And that sets the specs on some of the LEDs. But just remember, anything bigger than 0.007 is a pretty big color shift. If we look at the spectrum, here's the power spectrum again, measured almost 3,000 lumens from this, and a radiant flux of 8.85 when I'm running this at 400 milliamps. So I'm going to skip over LED module 2 for a minute. We'll come back to it. And I'm going to go to number 3. So number 3, now we're starting to see some issues. There's clearly 4 LEDs that are blue or purple. The rest of them seem to be okay at this level, but there's certainly 4 that have an issue. And if we look at what that does from the color point, it takes it all the way from the black body here at 4,000 down to this big black square, still kind of a pastel color, but starting to trend purple. And the magnitude of this color shift is 0.095, which is 10 times greater than that of what I showed you before. And if we look photometrically at what is happening, the blue peak intensity is actually increasing and the phosphor emission intensity is actually decreasing. And the net result is that my luminous flux is dropped. It's about 80% of module 1. But this is a little surprising. My radiant flux, the total amount of radiant power coming out of the device, is actually going up. So let's continue and look at some more. This is sample 4. Now we have even more failures. We see some variations, definite purple, blues, maybe a little pastel. Our color point has moved into the purple realm of colors, where we would expect a combination of light that we would expect to give us purple. And this color shift is 17 times greater than that first module I showed you. Our trend of the blue LED peak increasing is continuing, and the phosphor peak emission is decreasing. And now we're at about, I think this is getting close to a 30% loss in luminous flux, but the radiant flux is still higher. So we're putting out more radiation. It's just more blue light that the eye cannot use effectively because we're losing this phosphor emission. Here's module 5. Story continues even deeper into the purple segment. You see most of the LEDs now are having significant issues. And our color shift is 28 times greater than that first module that I showed you. The luminous flux is now almost half of what module 1 was. So a significant reduction of luminous flux because we're losing this phosphor emission. We're getting a lot more blue emission from the device. Our radiant flux still continuing to go up. And the last one I'm going to show you, this is one that's just about the whole device is having issues. There might be one LED that's okay, but just about everything is having an issue here. The color point is not quite to 450, which you wouldn't expect because there is still a little bit of blue light, but it's pretty close to it. So this is a significant color shift. See, 0.408 or 45 times greater than the first module that I showed you. So this is a very large color shift. The spectrum, you mainly see blue. There's just a very, very weak phosphor peak, hardly anything. And as a result, the luminous flux has dropped down to 555 when it should be around 3,000. But the radiant power is still going up. So if we look at all the samples and map their color points, we see a steady progression from this first sample that I showed you, very close to the black body, right down a straight line, right to the blue color point. And this is proof that we're getting more blue radiation out of these devices and we're losing phosphor. But we haven't gotten into why that's happening. Well, a couple of things could be causing it. For example, is heat an issue? Are these LEDs getting too hot? Well, it turns out heat's probably not a significant issue. And the reason I say that is twofold. First, as I showed earlier, the radiant power of these devices is actually increasing. If the LEDs themselves, the blue LEDs, were being damaged, you would expect the amount of radiant power that they produce to decrease. But that's not the case here. The blue LEDs are emitting blue light. The issue is there's not the phosphor layer there to convert it. The other indication that there is not likely a significant heat issue is there's no obvious discoloration around the LEDs. There's no signs of burning or charring that would happen. And also, I didn't cover this earlier, but this is coming from a blue LED. The purple light is coming from a blue LED, and it's because of the combination of blue and yellow. It's not a violet source, which would be 400 emissions at 400, 410 nanometers, and it's not an ultraviolet or a black light source. It's coming from the blue LED. So here, just to kind of recap that, so here's how luminous flux changes. You can see we have some samples. If we think of an L70 or the point where the luminous flux is 70% below its initial starting point, you can actually have a fairly large color shift for these samples. So 0.015 and still be above that L70 level. So just looking at luminous flux alone is not sufficient to understand these failures. You have to look at the color change as well. And as I mentioned, the radiant power is increasing as well, which is saying the LED is doing its job. It's just the other parts of the system. If we look at the impact on color rendering, so color rendering is on the y-axis here, and the amount of color shift is on the x-axis. You can see till we get to about this 30% point of luminous flux, the color rendering stays pretty stable, but then it just falls off a cliff and just degrades rapidly for some of these samples and actually becomes negative. And when you have this decrease in CRI combined with glare, can pretty much assume that driver response may be affected by these changes in the fixture. So this is definitely not a good situation and something we'd like to avoid going forward. But what's causing it? We hadn't gotten into that detail yet. What's going on here and how can we understand it and prevent it from happening again? So here is actually LED module 2. So my colleague Steve Paolini actually did this analysis. It's very nice analysis. Took off the frame, the lenses, and everything. And so this is just the PC board with the individual LEDs mounted on it. You see they're numbered here. You can see right away in this sample, LED 14 is missing its phosphor layer. There's a little yellow debris there. That's probably the phosphor. The rest of them look okay. And what Steve also did was put this module under in a room with fairly low light levels, and just turn the LEDs on to 15 microamps, just enough to turn them on, but to allow him to take pictures of the LEDs without saturating the camera. If you have the current too high when you do this, you'll actually saturate the camera and everything will look white. But what you will see, obviously the device with no phosphor is just a blue LED, so it emits only blue. But if you look closely, you'll see some of these other devices have these little cracks in the phosphor layers. Some of them are bigger than others. These two down here, 17 and 18, actually have cracks on the side, and there's a little bit of blue light leaking out the side of the device. And these cracks go all the way through the phosphor layer from the top to the bottom, and that's the critical thing. It goes all the way through the phosphor layer. So the blue light emitted from that portion of the LED travels directly out past the phosphor layer because there's no phosphor on top of it. It goes right up that crack and gets emitted as blue light that we can see in this nice little experiment. Another way to look at this, if you start to sort the boards, you can start to categorize the LEDs on the board. There are some LEDs, these are measured in Steve's lab at room temperature 15, or room light in 15 microamps, and a reduced level of room light, which gives you a little bit better contrast. You can see there are some that are fine. There's really no issues with them. Some of them have maybe beginnings of a crack, but it doesn't go all the way through the phosphor layer. And so there's no blue light emission. And some just have a little bit of crack that goes all the way through. So we're getting some blue light through this phosphor layer, more than what the manufacturer intended. The manufacturer wanted the LED to operate like this, not with these top to bottom cracks. You can see some cases the cracks get even worse and you get more blue light out. So the length of these cracks, the width will play a great role in terms of determining how that blue and yellow emission changes from the LED. I also looked at these in my labs for more samples that had the 4 color shifts, and I saw the same fine cracks that Steve did. Also some pretty significant fractures, like whole sections of the phosphor layer missing, or large cracks. In some cases, it almost looks like the phosphor layer blew up or something, and there's large chunks missing. And there are, of course, those where there is no phosphor layer at all. And sometimes, if you look close by, you will find the phosphor layer sitting near that LED. So phosphor just basically delaminated and is resting on the board as debris nearby the LED. And so if you think of the impact this is going to have on the color shift, if my LED doesn't have these top to bottom cracks, it's going to be a white LED, and that's what the manufacturer intended. But when these cracks appear, start to get a little bit more blue in there, and it starts to shift, And if it gets really bad, it's going to start looking purple because that's between, that's on my way to my blue point. And eventually it's going to turn blue once I totally lose that phosphor layer. Just to confirm that the LEDs aren't getting too hot, we did some thermal imaging as well as measurements with thermocouples. And what we found was that they're not getting too hot. This is not a heat issue per se. This is a fundamental issue with this particular LED. We also know that the blue LED is doing its part because of the radiant power increasing. But the phosphor is just cracking off and delaminating, as I said. So if we look at the root cause of this, we have these fine cracks in these types of products. These fine cracks are appearing in these silicon phosphor layer that have these excessive blue color shift. And the key thing is these cracks go all the way through the phosphor layer and expose the blue LED underneath. And so that portion of the LED emits light, the blue light directly, never gets converted by the phosphor. So you don't have the broad spectrum for that portion of the LED that you want. You just have blue emission, and that reduces your lumens and also impacts the color rendering. Now, as we saw, not every LED in the source is affected to the same level. There's varying degradation. Some LEDs are fine, some have failed catastrophically. But when we think of this as a light source, the light that hits our target is going to be the accumulation from all these LEDs. So if some are off, that's going to skew the light that we're seeing. Now, it's also important to know that, as I mentioned, that it's critical to maintain adhesion between this silicon phosphor layer and the LED chip. And this appears to have been negatively impacted. So we're thinking the silicon binder is becoming brittle over time because there is this visual evidence of damage, cracks, gross fractures. So certainly there's some brittleness in that layer that you would not want to be there. And in extreme cases, the silicon phosphor layer may totally separate from the LED. And in that case, all you have is a blue LED, not a white LED. So, is this common in LED packages? Not to this extent. This is kind of a rare occurrence, but you can get small shifts along the line between the blue color point and the yellow color point in phosphor converted LEDs. But based on historical data that I've seen, these shifts are usually very small, usually on the order of 0.007 or less. They're not the significantly larger 20, 30 times X that we're seeing here. So you can get fine cracks in an LED, and that's not necessarily an issue. The fundamental issue here is the cracks go all the way through the silicon phosphor layer, and that is not common in an LED. So these cracks will depend on, of course, the material that is the phosphor silicon is made from. It will also depend upon the operational temperature and currents. But manufacturers are aware of this, and they make every effort to preserve adhesion between the LED chip and the phosphor layer. So if we look on if you're interested in getting more information on color shift in LED packages, you can go to this web link here. It'll be on the last slide as well. But there's a lot of information that the LSRC has collected over the years on color shift in LED packages, and a lot of it is captured in these publications. So the key to understanding what is the potential for this to happen in products that you're specifying or buying is to look at the LM80 data. But I'm here to tell you today that not all LM80 data is equal. The original version of LM80 that came out in 2008 focused on lumen maintenance, but did require manufacturers to give a delta U prime, V prime, or a color shift value at each measurement interval. You can see here's the cover for LM8008, measuring lumen maintenance of LED light sources. Well, the people that worked on this realized that wasn't really sufficient, and LM80 was revised in 2015. You can see that's reflected in the title, measuring luminous flux and color maintenance of LED packages, arrays, and modules. So color maintenance was added to LM80 in 2015. And to accommodate color maintenance, the manufacturers are now required to report U prime and V prime at each measurement interval. You say, great, we've got a new standard. People just tested that. Well, it's not that easy. The standard has to be accepted. People have to request it. There's also the issue with legacy products that were tested under the old format. So it happens to turn out, I did a study on LM80, and I specifically asked manufacturers for LM80 15 data. I did the study in 2020 with Monica Hansen, and even in 2020, the use of the LM8008 format was very common. And if you remember, I told you these LEDs were made in 2017. We know that from the board date code. So they were likely tested to LM8008 and not to LM8015 because that hadn't really been spread through the industry very well at that point in time. But fortunately today it's later. So today when you're speccing, be sure it's LM8015 data that you're getting. If you have the LM8015 data, you can look at the U prime change. You can look at the U prime change, and you can just plot it out and graph it. You can also model it. We know about TM21 for modeling luminous flux maintenance. If you're not familiar with that, here's a link to the IES official calculation tool for calculating luminous flux maintenance from LM80 data. There's also a TM25, which is less well known, but is used for projecting color maintenance of LED modules as well. And there's some limitations to TM35, I'll admit up front. But one of the good things it does is it provides graphs of this change in delta V prime versus time and delta U prime versus time. And this gives you the opportunity to see how this LED will change over time and how the color will shift. Remember, these LEDs that we were looking at, the color shift, the delta V prime component was a lot more sensitive to change than luminous flux maintenance. That's not always the case, but for these samples it was. So best practices. If you're thinking about buying or speccing a fixture, be sure you understand what LEDs are used in that fixture and what level of experience the LED manufacturer has with that package. LED manufacturers tend to have packages that they're very good at making and some that they're just new to the market that they're trying to catch up on. And so make sure that the LED manufacturer has experience with that package and lots of units out in the field. You want to be sure LM80 data is not just a simple check mark. You want to make sure it's LM8015 or later, and pay attention not only to luminous flux maintenance, but the chromaticity shifts, the delta U prime and delta V prime over time. And if you really want a full analysis, TM35 can do that for you. The other thing about LM80, we all know LM80 data is 6,000 hours minimum. That is the minimum, and often manufacturers will test for longer periods of time. You can always ask if they have that test and see what that data says as well. A couple of other things to remember is a good LM80 report will give you different currents and different temperatures, and these represent different stress conditions for the LEDs. A low current and low temperature is a very low stress environment. A high temperature, high current is a very high stress environment and will likely degrade the LED quicker. So you want to be cognizant of that. And so when you're looking at the LM80 data, sure, I know there's charts and charts and charts, but you want to focus on the ones that are relevant to your fixture. So what's the current your fixture is going to be operating at? What's the temperature? And so the operating current you look at in the LM80 report should be equal to or greater than that of the fixture. And likewise, the temperature should be equal to or greater than that of the fixture. You don't want to look at a low current, low temperature stress environment for a fixture that you're actually going to operate in a higher current, higher stress state. That will cause some issues. So where can you get this data? Obviously, the LED manufacturer can give you information on the package specs, LM80, TM21 projections, and you can ask them about what type of experience they have with this package. The fixture manufacturer is going to tell what the fixture operation specs are, the warranty information, what LED they're using and why, but they may also have models that they've developed through their own testing of how this LED will perform. And so you might want to ask them about that. And as a field engineer, you can verify the lumen maintenance performance meets your demands and the color chromaticity is going to be acceptable for your application. And when in doubt, you can do field measurements just to see how the luminaires are changing over time. So just to conclude, these purple street lights are caused by top to bottom fractures of the silicon phosphor layer in individual LEDs. Fractures start as small cracks and grow in size, and the more they grow, the more of the blue LED underneath they expose, so the more blue light you get from the device and less phosphor conversion. And so the way to check for this is to look at the LM8015 or later data for both lumen maintenance and chromaticity maintenance. And if possible, ask for the longest test duration that the LED manufacturer has. 6,000 hours is a minimum. Often they have more than that. And you want to look at aggressive conditions that are higher than what you're using in your fixture, higher currents, higher temperature, just to make sure your fixture can hold up to that. And there are, of course, IES tools for projecting luminous flux maintenance and chromaticity shift over time, TM21, TM35, that can be used as well. So with that, I'd like to conclude, and I'd like to thank all the members of the LSRC for their help in pulling this talk together and their participation in this evaluation. And if you're interested in more information on the LSRC, please contact my collaborator, Morgan Pattison, at morgan@sscelinc.com. Would also like to thank the North Carolina Department of Transportation for useful discussions about street lightings and providing the samples. And Steve and I would like to thank RTI International and Telelumen for providing equipment that we used in this analysis. And this last slide, as I promised, here is a list of some publications that the LSRC have put out through the years on LED luminaire lifetime, the impact of color shift, and the study of lumen and chromaticity maintenance taken from LM80 data that Monica Hansen and I did. So with that, I'd be happy to answer any questions.
Well, thank you, Len. A very interesting presentation. We have several questions in the chat, and at this time, I'd also like to set a reminder that you can include additional questions in the Q&A section, and any questions that we don't get to, we'll respond to in an email. First question, Len, can you show where U and V are on the LM80 report?
I don't have a report in front of me, but the way it's generally grouped There will be a current and a temperature. So there will be tables. So one table will be lumen maintenance at a set temperature and current. The next table will usually be delta U prime V prime, or the magnitude of the color shift. The next table will usually be U prime. The next table will usually be V prime. And then after that will be another temperature and current. I should also like to add, I think my collaborator, Steve Paolini, is online. So Steve, if you want to turn your mic on and help answer with these questions, please feel free to, or to make any additional comments that you may have.
Okay, I'm here. I don't have anything else to say on that particular thing, but I'm here.
All right, thanks.
Okay, Lynn, we have another question. Have you communicated your research findings to the manufacturers of these luminaries or LED modules? If so, could you describe their response to your report?
We have talked about this with the fixture manufacturers that we're aware of. I know Morgan Pattison was actually the ones that relayed this information. And, Morgan said that the manufacturers were receptive to it. They understand the issue. They've worked to address it. I think we've seen that in some other things, some other publications where the industry is aware of this and are looking to address it through warranty replacements and other means. I think there are also other manufacturers that I'm aware of that had done their own testing, and this is why I ask the fixture manufacturer what type of testing they did. There are manufacturers that I'm aware of that did their own testing on these LEDs when they were first introduced and realized that they weren't suited for an application that you expected to stay in the field 15, 20 years or so.
Okay. And we've got another question along with that. Could you share your insights from your contacts at the DOT or utility companies regarding the failure rates of LED lighting modules? Have these failures peaked, and how has their frequency evolved over time?
This is a good question. I don't know what the failure rates are. Obviously, there was significant failures that have been happening in the last 2 or 3 years, and it's not all LEDs, it's not all fixtures, but it certainly is a significant portion of them, and that's why the problem's so visible. So I don't have hard numbers on what the failure rates would be. This is likely a latent problem that hopefully is working its way out. We were kind of in that when these products were introduced. We were in that realm where there was a standard to specify chromaticity coordinates, but it wasn't being used as widely, and people weren't as aware of it as they are today. So hopefully a big part of what we're trying to do here is get the word out that it's not just luminous flux maintenance you need to think about, it's also the color stability of the light source as well. So it looks like Willem thinks the failure rate's somewhere around 10 to 35%. So that's Willem van Driel. So I would trust Willem's numbers.
That is my guess. That's my guess, Lynn.
Sounds good.
If I see your, the root cause analysis and so, I think they have, there is a lot of money involved. That is what I guess. So I hope they are well insured. You can insure against this, but they will be really hard to get the money returned from an insurance. Wow.
Okay.
Did you notice my other question as well or not, or is that up to the admin? I guess, right?
I didn't see your question. What was your question, Willem? Since we have you on the line.
Yeah, you kind of the holy LM80 and TM35, right?
Yes.
TM35 I think is fine, right? Nothing wrong. But the LM80 is not holy, yeah. So because many LED manufacturing are using active cooling, so they actively cool, and with the CSP, where the phosphor layer can be quite hotter then you think. And if you control the temperature in the way it currently is done in LM80, or some suppliers do, or what they are allowed to do, then you cannot foresee this issue. So that is a little bit tricky, I think.
Yeah, good
Yeah.
point. Good point. I mean, certainly there are people who do LM80 data that's more useful to the fixture manufacturers than others, and I understand your point. We do have to be diligent about understanding how that LM80 data is acquired.
Yeah. So yeah, there is no control yet in LM80 that you can control the solder temperature as low as you can, but actually we should rewrite and tell manufacturers that it should be at least 10 degrees different.
Mm-hmm.
Not within the 10. That is a little bit what we internally did in Signify and years ago, that hey, you can control, if you suck out all the heat from the bottom, right, actively, then the junction is not getting hotter and your phosphor crunching is also fine. That's why we said no, we shouldn't allow this temperature control so actively. Yeah.
Okay.
Nice work, Lynn. It's nice work. This.
Thank you.
For
Thank you.
one person retired, right? And,
All right, Lynn and team, we've got quite a few more questions coming in as well. We have one. What is the mechanism causing the cracks in the adhesion of the silicone phosphor layer to the blue pump LEDs?
Don't know exactly. We'd have to do some chemical analysis of the silicone. In general, you can think of if the silicone overcures, it could get brittle. So there could be some issues like that, or it could just be the silicone they chose just wasn't the right one for this application.
Okay. Next question. Is this problem isolated to or more likely to happen to chip scale package type LEDs?
We don't know that. So there are certainly manufacturers of CSP packages that make very good CSP packages. And as far as I know, and Steve, maybe you've got some perspective on this as well, this issue hasn't appeared. It certainly appeared in these packages. I certainly haven't seen this type of phosphor failure in other packages, although sometimes if you run COBs, it can happen. This issue can happen if you run them, especially high currents and high powers. So Steve, any additional thoughts on that?
Yeah, not much. I mean, I think you covered it, but I will say, and you said it in earlier, the CSP is the newest of the packages that have come out. So there were probably some early things that people didn't understand about it. I don't think it's fundamentally more susceptible to this, but may have been in the early times.
Here's another question, and this is actually one I asked you the other day, Lynn. What causes the shift to a greenish color that we see at gas stations and some parking decks in the triangle?
Okay. A good question. So there's actually a lot of information in those references that we had that I had at the end of the presentation, but actually a green color shift is usually caused by a change in the phosphor. Or one way to get a green color shift is through a change in the phosphor. So if you think of the white color point as being a balance of blue, green, and red, if you start to lose a little bit of red, your color will shift green. So it's a totally different mechanism than what we saw here, where you're shifting along the blue-yellow line. So if you, for example, if you have a warm white LED that has a red phosphor added to it that's moisture susceptible, that red phosphor may quench over time and not emit as effectively, and so you will tend to see a little bit of a green shift when that happens. So that's one way you could get a green shift in an LED device, and that's actually because of a change in the phosphor itself.
Okay. Next question here, and I know we're a little over on time, but as we have some questions, if you guys are good, we'll continue with them.
Sure.
Have the failures been consistent across the different LED chip manufacturers?
As far as I know, that's it's not necessarily the case. There are certainly some manufacturers that are more prone to this than others. I think by this point in time, hopefully they've got their processes figured out where it's known. Certainly, LED package manufacturers that make very good products that are not prone to color shifts of this magnitude.
All right, we have, where do we find the LM80 information for specific fixtures? Seems like TM21 is available on the spec sheet, however, that's not a direct correlation to LM80, correct?
Right. So the TM21 projections are derived from LM80 data. So you can ask your fixture manufacturer for the what LED they're using, who makes it, and they should be able to provide you the LM80 data for that LED. And it's important that you get the LM80 data to at least LM80 15 or later.
Okay, I think we just got another one. Is the issue seen in other countries such as Canada or?
Yeah, it's definitely in Canada. I also saw some indication that it was in Ireland, so it seems to be parts of Europe as well. I don't have any information on the prevalence there, but it's not just the US.
Yeah, I could interject one thing, and this goes back to you were mentioning about it's not specifically a heat issue. So we didn't notice, at least in the data reporting, that sort of hotter places had a higher incidence or colder places had a higher incidence. So that's just another indication that heat was not the primary problem.
Mm-hmm.
We have a question. Can you tell us which LED manufacturers were used in the streetlights you evaluated?
I don't think I can disclose that, unfortunately.
Okay, understood. Just a quick one. What are field replacement of the defective streetlights typically handled, or how are they typically handled?
That's not quite my area of expertise, but I know here in the state of North Carolina they have a contractor that does the field replacements when the problems are identified. I will also add, I know here locally, if you go on the Progress Energy website to report a faulty street light, they actually have one of the failures, blinking, it's not on at all. They also have purple street light as one of the potential failure modes where you can, so at least ways here locally in North Carolina, you can directly report to the utility company that you've seen a purple street light.
Great. Well, that concludes the questions in the Q&A chat. Just a reminder, I've placed in the chat that you can ask additional questions and email to iesriley@gmail.com and ldavis.emeritus@rti.org. And just a secondary reminder that the presentation will be archived on the YouTube channel, which is also included in the chat as well for your convenience. And we're thankful for all of our continued members and participation in today's webinar. We hope you enjoyed the webinar, and please look for the upcoming presentations. Keep an eye on your email. And thank you again for your time today. Hope you enjoy your rest of your day.